Hello, everyone. This is Adam Pentar with the Statistics Division of the ASQ. I'd like to welcome you and thank you for joining us. Our speaker today is Matthew Barcelo. He's joining us all the way from Germany, the wonders of holding webinars. It's terrific. We really appreciate it. He's been the editor of the Statistics Division, so the ASQ Statistics Division's Statistics Digest, since 2014. And the title of the webinar he'll give today is Empirical Root Cause Analysis. All microphones other than the presenters have been muted, so if you have any questions or comments during the webinar, please use the questions interface in the GoToWebinar control panel. Matthew will address questions at the end of the presentation, so he will leave some time to do that. At this time, I'm going to hand things over to Matthew, and I want to say thank you to Matthew once again for presenting with us.
Okay, so hello and welcome. I'm going to be presenting.
Are you going to share the screen?
My screen, yes,
yep,
that might be a little bit better.
There we go. All right.
Okay, so I'm going to be presenting, as you can see on the screen now, empirical root cause analysis. Before I start, I want to mention a lot of you might be thinking empirical root cause analysis, there's no point in talking about that. Every root cause analysis should be empirical. And if that's what you're thinking, I completely agree with you. Unfortunately, it's been my experience, it's not always the case. And that's what I want to talk about. I was going to say tonight or this afternoon, depending on where you are. So first I'll talk about why do we perform a root cause analysis? Because I'm talking about root cause analysis. We typically perform this when we have the failure of a product or process. But I'd like to point out these same principles I'm talking about here also apply for product or process improvement. Suppose we want to know why a system's performing the way it is at the moment. It's not a traditional failure root cause analysis, but what I'm going to be presenting does apply there just as well. Now, a little bit of background, there's already many tool sets available for root cause analysis. The 7 quality tools, Ishikawa diagrams, run charts, scatter plots, the 7 management tools. They're management tools. They can also be used for root cause analysis. There's many other quality tools. There's also calipers, microscopes, chemical titration, hammers, and yes, hammers. I'll get to that a little bit later. The toolkit for root cause analysis is a wide toolkit. But I want to present first a hypothetical example based on a not so hypothetical consultant. I met this gentleman some years ago. We were discussing a situation. To illustrate it, I created the example of a hypothetical quality failure. The hypothetical failure was a plastic component breaking during assembly. I drew a drawing of it on the board. And the not so hypothetical consultant explained to me the proper way to perform a root cause analysis. Apparently I was doing it wrong. I was talking about empiricism. First you do a failure modes and effects analysis, and then you do a quality function deployment. Quality function deployment, generally done when you're designing the product or process. Shouldn't you look at the part? And our root cause analysis needs to be empirical, was my response. And he told me the quality function deployment is empirical. You need to go into production and look at the work instructions, which I think is not always possible if you're just coming up with a design concept when you're using a QFD. Also, my thinking is if you're in production reading the work instructions, which is not necessarily a bad thing to do, while you're there, please take a look at the failed part. The example we were discussing was actually 1 out of 1,000 parts breaking during assembly due to insufficient material thickness by design. In this hypothetical scenario, the work instructions would not have led to the root cause. Just observing the process for a few minutes could give useful information, but chances are the failure is not going to happen then and there. It's only 1 out of 1,000. This is a sketch, or a recreation of the sketch I drew when discussing the situation with my consultant. Performing a FMEA, that's not wrong. Looking at an FMEA, also not a bad idea. Checking the work instructions. But he did not see the need to look at the defective component. Why? Because we'll do the FMEA. But please look at the drawing there. The area that was breaking had a very thin wall thickness. Maybe that thickness is related to the failure. By design, it should have been thicker. That's not information we could have gotten if we discussed the part. Imagine, nobody's ever seen the failed part, and we're brainstorming ideas. I'm not knocking brainstorming, sometimes you need to do that, but the empiricism, look at the part. That's why I'm talking about empirical root cause analysis, and I unfortunately do see a need to discuss that topic. The consultant's not alone in neglecting to mention the need to actually look at the part. I've read a lot of the literature, and a lot of the literature seems to explain the team should sit together and use quality tools to find the cause of the failure. Not a bad idea itself, but they fail to mention what Dorian Shinen said. Talk to the parts. They're smarter than engineers. We need teams, we need tools during root cause analysis. In my view, the most important team member is actually the defective part. And I will say, if available. Much of the literature has what I call a deus ex machina approach. According to Merriam-Webster's dictionary, that's a stage device in Greek and Roman drama in which a god appeared in the sky by means of a crane to resolve the plot of the play. An actor or actress was lowered down, fixed all the problems, and everything cleared up. And for me, that's, well, let me go ahead and show you. The root cause analysis equivalent would be engineers and production workers sat down at the table and realized the root cause was, well, let's look at the part. What evidence is there? What does the data tell us? We can then generate hypotheses, the result of a brainstorming session, but they should be data-driven. Evaluate with empirical data, not just sitting at the table. And I've seen this repeatedly. Somebody has an idea what the cause is based on perhaps prior experience or just general knowledge, and they implement a change in the process or kick off a design change. In 3 months, we'll validate the parts and then know if it worked. Well, maybe we should go back, look at the failed part, find a hypothesis that explains it, and test that. And here's a quote that I think is very appropriate to root cause analysis. It's attributed to William Thomson, Lord Kelvin. I say attributed because empirically, I don't know if he actually said it. It's very difficult to track down in the original source of the quote, but I think it's very relevant here. When you can measure what you are speaking about and express it in numbers, you know something about it. When you cannot express it in numbers, your knowledge is of a meager and non-satisfactory kind. Now that's Victorian English. In modern English, that would mean when you have data, quantifiable numbers behind what you're discussing, you have more knowledge. Let's think of this. If I told you the part is failing, well, we know something. We know it failed. It did not work, but that's not really much to work with. But what if I said 17 out of 20? Now we've got more information. Let's take it to the next step, and I said the 10 millimeter dimension plus minus 2 millimeters is measuring 14 on 17 out of 20 parts. We have numbers behind it. We have far more knowledge. The root cause analysis needs to be empirical. However, we don't need new concepts there. The tools, the methods, the concepts, they already exist. We have the scientific method. Box's iterative, inductive, deductive process, and Deming's plan, do, check, act. I believe these three concepts can be combined into one simple approach for root cause analysis. What I don't want to do is give you a formal procedure. I want to give you more of a thought concept, the actions that must be taken during a root cause analysis, regardless of which type of procedure or process you are following. So first I'll discuss the scientific method. However, I'd like to mention John Tukey's Exploratory Data Analysis. This fits here especially well. In exploratory data analysis, you explore the data graphically. Now, if you have no data to explore graphically, for me, the first step, if possible, is collect data, then graph the data. Now, once you've graphed that data and looked at your part, what is your tentative hypothesis? And I say tentative hypothesis. We could call it a working hypothesis. I won't correct you if you were to call it a theory. I suppose we could call it a well-founded guess, but my preference is tentative hypothesis, our first idea. We form it based on the available data. These, from my view, are the ideas that we list in our Ishikawa diagram or cause and effect diagram. It's nothing more than a collection of hypotheses that could explain our failure. Now, to have a good hypothesis, it should be simple and general. The more specific your hypothesis is, the more likely it is to be wrong. If you build one hypothesis upon another, if any one in that chain is wrong, then you're wrong. Now, sometimes it's necessary to do that, but keep it as simple as possible. Do not make too many assumptions. And the next 2 points, I think, are the most important. It should be refutable. In other words, it should be possible to test your hypothesis and reject the hypothesis. If you can't reject your hypothesis and all you can do is confirm it, there's no way to really trust it. You can't evaluate it. And it should make a prediction. These two go together because your prediction is what you would expect to see at the end of your evaluation. You should also have objectivity and the ability to predict. P.B. Medwar reminds us that experimenters must be resolutely critical, seeking reasons to disbelieve hypotheses, perhaps especially those which he has thought of himself and thinks rather brilliant. And I think this is incredibly important for us to remember. This, for me, means beware of the pet hypothesis. It may turn around and bite you. And we're human, I'm human, I have the same problem, but I'm aware of it and I try to work on it. You try to keep an open mind. You do not want a preconceived notion. In other words, a pet hypothesis. There's always the risk. You're convinced your hypothesis is true and you interpret all of the data and evidence through the lens of that hypothesis. So being people, there's a risk that we could do that, so we just need to be aware. Am I favoring my hypothesis? Am I interpreting data in a way that supports it when, if it wasn't my favorite hypothesis, I would be a bit more critical. If you really want to know if you can trust your hypothesis, put an effort into trying to prove it wrong. And Adrien de Groot says, if one knows something to be true, he is in a position to predict. Where prediction is impossible, there is no knowledge. If you have a hypothesis, I hypothesize something simple. The parts are failing due to a measurement deviation on the length. I can easily test this hypothesis. That's great. Now it's refutable. And I have a prediction. When I measure the failed parts, they should have a measurement deviation on that length. Richard Feynman tells us to avoid preferring one result over others. Maybe the results we like are just the results of dirt falling into the experiment, in his words. Something went wrong with the test. I've actually seen this once before in a situation. It was a noise. Everybody was convinced it was a metal clip. And I swear to you, I wasn't trying to play games with my colleagues, but I disassembled the clip to take it and measure it. And they were all saying, look, the problem's there. It's got to be that clip. And then they showed me, we still have the noise. See, the clip is causing it, but the clip was in my pocket. I almost said secretly. It was not intentional, but the clip that was causing all our problems had been disassembled, and the problem was still there. There was dirt in our experiment. Luckily, we caught that. I awkwardly pointed out, but the clip's here. It can't be. We may also have the risk of discarding accurate results because they were not what we wanted to see. And blinding can help us prevent inadvertently selecting the results we prefer. Having a second person to interpret the results helps. I've done this myself when I've taken measurements. I know exactly what value to the decimal place I want to see there, and I know I want this, and I did not trust myself. A little bit too much pressure and I might actually have that. So now it's all in fine motor skills. No, okay, here, I handed the part to my colleague and asked, could you please measure this? Let's see what you're getting on this to confirm my results were correct. And indeed they were. Now there's many approaches to the scientific method. If you know another approach and use yours, that should work as well, but for the presentation, I don't want to put 5 or 10 different variations on this. Myself, I think I first learned of the scientific method in grade school. That method would probably still work here. But I'm going to go ahead and present the variation based on John Platt's strong inference. He explains that to do this, we devise a hypothesis, devise a crucial experiment, or several of them. And in my experience, often it's a series of experiments that will lead us to the underlying root cause. Devise a crucial experiment with outcomes that will exclude one or more hypotheses. So even if you can't confirm your hypothesis, excluding others helps. And you want one that could potentially reject your hypothesis. Then carry out the experiment and get a clean result. And repeat the procedure. It's an iterative process. Often we're wrong, hopefully we learn something, and then we move on. Take another hypothesis. Think of it this way. You just tested the hypothesis measurement deviation, and the parts were in specification. Well, I may have a new hypothesis. Maybe the specification was wrong. Or I would go to my Ishikawa diagram, find the next idea there, take that one, and evaluate it. Experimentation is sometimes necessary during a root cause analysis, and I use the word experiment very liberally. It's a formal experiment in a laboratory or taking a look at the part. Also, attempting to recreate the failure under simulated conditions I find is very informative. It's not definitive. Just because you can recreate it under controlled conditions does not automatically mean it's the same as the actual failure, but it's informative. You might learn something new. It may lead to the root cause. It may lead to eliminating potential root causes. It may lead to new insights that will provide you with the root cause. And of course, be sure to control your variables. I find it's an international hobby of engineers around the world. Okay, so it could be option A, B, C, or D. Let's change everything at once and see what happens. And I'm not talking about design of experiments. I'm talking about we just changed everything, tested it, and then said, we were right, it worked. Yes, but which one? Don't change all your variables at once outside of a DOE. I will say there is an exception to this. Occasionally, I have actually intentionally changed everything at one time, knowing I will not have conclusive results, but I had many options at once. I can't confirm which one it was, but if it's none of them, I can find out a little bit quicker. We can use deduction and induction, and when I use this terminology, the terminology is not what's truly important. It's what's behind the terminology, the meanings. Deduction, it uses what's known to form a hypothesis, is used to form a hypothesis based on what is known. It goes from a conclusion. It forms a conclusion based on a general premise. Induction is used to form a new hypothesis based on observations. It uses empirical data to form a general conclusion. Now, please do not ever stand there analyzing your problem and stop and think, now I need to go look it up. Was it deduction or induction? No, it's the actions that matter, and I will show you how to perform these. Use boxes as iterative, inductive, deductive process. The process is repeated until the root cause is discovered. This is not the original illustration, but this is a very close one, and I think it explains it very well in terms of terminology. We have observations, measurements, experiment results, or someone handing you a customer complaint with photos and a defective part. There's a discovery there. We get our first idea. That's why I said a tentative hypothesis. You can call it theories, call it conjectures, call it ideas. Now, how do we interpret that information in front of us? What is our hypothesis? Now, let's test it. Look for the justification. After we've tested it, we look at our results, experimental results or measurements. Now we interpret it. That's the discovery phase again. Think about it and reevaluate. I say in root cause analysis, it's okay to be wrong. You just want to be wrong as quickly as you can, and I will qualify that with in the most economical manner possible. If you have two hypotheses and one is more probable, generally you test that first, but if the more probable one requires $100,000 in testing in a three-month test cycle, and the other is measurement deviation I can check with calipers, check that one first. But think of the Ishikawa diagram. You can go to the Ishikawa diagram, list all your hypotheses, and then you prioritize them, take them, and they fit in this model. Test that first one. If it's wrong, okay, go to the next one. The target is be wrong as quickly as you can. I know, at least in my case, if I go to my boss and say, yeah, in the past 2 days I investigated the issue. My first 7 hypotheses were wrong, but I found the root cause. What he's not going to hear is, I was wrong 7 times. He's going to hear, we got the root cause and confirmed it. And I expect it's going to be that way most of the time. It's also an iterative process. So I think plan, do, check, act, and Box's iterative, inductive, deductive process makes for a very long term, but it can bring the concept together. For quality improvement, we use plan, do, check, act. It fits in root cause analysis as well. Describe the problem and gather data to form a tentative hypothesis. That first information. Here's a step I haven't addressed before, describing the problem. For me, that is one of the most important steps in a root cause analysis. The problem description. The part failed. It's easy for me to explain. The root cause is it didn't work. No. How many units failed? What are the measurement data? What did I say before? If you can describe it in numbers, you have understanding. Bring that into your problem description. Clearly define the problem you are analyzing. Think of the problem description as the statement. Well, it is a problem statement where if a new member suddenly joins that team, you can hand them that problem statement and they know what problem you're dealing with. If you need to present it to your management, they will know what the problem is. If you share it with your customer, it shows them you understand their problem. Describe the problem, gather that data, form the first hypothesis. And when I say gather the data, this may mean look at the SPC data out of production, statistical process control, what were the values produced over the last period of weeks, or look at the failed part itself. Form that hypothesis, or the way it often works is the team does sit down, they brainstorm, fill out the Ishikawa diagram, which for me is a collection of hypotheses, prioritize that first one you're going to evaluate, and test the hypothesis. Then check your results and form conclusions. Interpret it. What do these results mean? Do they support my hypothesis, or do they reject it? And often, you might discover something new. I've had one situation where we had a blocked tube. Now, my hypothesis for that would probably there was dirt or maybe metal chips in the tube. So I would test my hypothesis. How? I would cut the tube open and look. And I would have been wrong because there was a dead bug inside of it. An insect crawled in, died, blocked the tube. Pretty sure we could have brainstormed all week. None of us would have listed dead bug in that Ishikawa diagram. So none of us would have found, through brainstorming, the actual root cause. And just by testing the wrong hypothesis, dirt, we empirically discovered the true root cause, bug. Now, 5Y. We then needed to investigate further, but that was the critical information because a corrective action to keep dirt out may not be the same as the one to keep bugs out. And if you have found your root cause, verify it. Make sure it really is the root cause. Try turning the problem off and on. If you can create conditions where the problem exists and does not exist, realistic conditions, then you probably do have the true root cause. Then begin improvements or repeat the process. Here is a real-world example of a quality problem using cycles of plan, do, check, act. Full disclosure, the original article was using plan, do, study, act. I interpret it through plan, do, check, act to explain it here. For those who would like to read the original article, and I do recommend it, it's Use PDSA for Crying Out Loud by Kevin Dooley in the October 1997 issue of Quality Progress. But like I said, it is a real-world problem, not necessarily a quality problem, but somebody addressed a problem they were having using cycles of plan, do, check, act with quality tools. The baby is crying during diaper changes. What else would a quality professional do to address this situation but use quality tools? Plan. We need information. Collect data on 15 diaper changes. Plot the data on a run chart. Now we're using a quality tool. Now let's check it. It appears to be random. So our first cycle was wrong. No harm in that. What do we do next? We decide to document every step, create a flow chart, observe the process to see if we can find potential causes, then brainstorm the potential causes, create a cause and effect diagram or fishbone diagram or Ishikawa diagram, list those potential causes, and then start evaluating them. Decide which ones we need more data on. They test the hypothesis, crying was outfit dependent. I think that's a good one. That would be my guess. The baby cries based on what the baby's wearing. So they start documenting this. They did a histogram. Correct data on crying of outfits? I'm sorry, that was actually a Pareto. From here it looks like a histogram. No particular outfit stood out, so it may have just been random. As statistics division, I'm betting somebody could get a really good statistical study out of that if they evaluated it long enough. Then they test the hypothesis that crying is related to needing more changes. So they did a scatter plot. Crying versus interval, nothing. Then they tested the hypothesis. Crying happens less when it's the mother than the father. And they determined that was the case. So they found the root cause. Baby only cries more when father does the changes. But 5why? Why does the child cry more when the father does the changes? So they plan to observe, what do both parents do? This is the go to Gemba part in quality. Go into production or go to the baby changing station. Observe what the two parents are doing. They determine the critical difference. And full disclosure, I'd read this right before I had my first child. It really helped me. The mother kept the baby's attention. Keep the child occupied during changing and don't just do a mechanical change. And babies apparently cry less. Amazing. This advice did help me in real life. But they identified attention-getting strategies, things the father could do, and more things the mother could do to improve the situation. And being a quality professional, of course, they created a run chart to evaluate the effectiveness. So now I want to talk a little bit about John Tukey's exploratory data analysis. EDA and the scientific method can be combined with the iterative, inductive, deductive process as part of Plan, Do, Check, Act for simplicity. That makes it easier, contrary to what that sentence may indicate to you. Gather data and explore it graphically. And I don't want to qualify every statement with whenever possible. I know this is not always possible. It's whenever you can. Now, I've given this talk before, and someone actually came up to me and said, I talk a lot about looking at the parts, but they're in the nuclear industry and their failed parts are radioactive. My suggestion was, well, if there's anybody you don't like, have them do it. And they explained that's not an acceptable solution. Okay, so if you can never touch your part, or maybe it's somewhere else in the world where it failed, or it was heavily damaged during failure, or somehow destroyed during failure, or that awkward situation, somebody misplaced the failed part, we still want to be as empirical as we can. What data do we have? Do we have measurement reports? Do we have data from other parts? Can we check parts out of the same batch? Because if you have zero data, you can call it a hypothesis, but then we're in the realm of pure guesswork. Get whatever data you can. And if you can get data, graph it. Look at it, interpret that graph, form a hypothesis, by the way, using induction. Then evaluate it empirically. If the root cause is not identified, use deduction. And again, don't stop and think, was it induction or deduction? No. Look, use the information you have, form that hypothesis, get an idea, a guess at what is causing the failure. What explains the evidence in front of me? Then, how do I test that? Test it and interpret the results. However, Sir Arthur Conan Doyle warns us, it is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. If we do our cause and effect diagram or Ishikawa diagram, before anyone even looks at it, we're working from our theories and ignoring the facts. It should be the other way around. So what I've done here is I created what I call the RCA helix, the root cause analysis helix. It combines plan, do, check, act with John Platt's strong inference, the scientific method in other words, John Tukey's exploratory data analysis, and Box's iterative, inductive, deductive process. And I see this, there's nothing new here, in my opinion, just the way it's displayed. So I wanted a simple mental model to give you to walk away from here with. Plan, collect and explore the data to form that tentative hypothesis. Do, evaluate it empirically, check, interpret the results. What do they mean? Did I reject my hypothesis? Hopefully we learned something new, either new information leading to a better hypothesis, or worst case, I learned my hypothesis was wrong, which is also valuable. Imagine the organization that has a hypothesis, goes straight to the corrective action, waits 3 months till it fails. It's sometimes good to know that you're wrong. Actually, it's good to know you're wrong as quickly as you can because you're wrong. Form that next hypothesis, repeat the cycle. Once you actually can support your hypothesis, verify it. Try turning the problem off and on. If you can turn it off and on, you have the root cause. Act by implementing the improvement. And that would move us into a more traditional plan, do, check, act. Again, there's nothing really original here except the packaging of these concepts. And I do think they belong together. I'm not trying to give you a formal process to implement, just a mental model. Regardless of what process you're using, hopefully these elements are there in one form or another. However, after saying that I don't want to give you a formal process, I'm going to show you a flowchart of a process. But again, think of this more as a mental model. And I want to mention containment. It's not a direct part of root cause analysis, but I have had a situation where I was discussing an issue with the team. We decided a containment action was necessary. Somebody pulled a part out of a box, found a defect. We as a team decided 100% inspection was necessary. Unfortunately, they found it 3 or 4 weeks earlier and waited till the meeting to tell everybody. Suddenly I decided maybe I need to talk about containment as well when I discuss root cause analysis. Problems discovered or an improvement is needed. Plan, what's our approach going to be? Who's our team member? Do we need a team? Do we need a containment action? And containment action for me often requires a team, even if it's an ad hoc informal one. Maybe I need to call someone from the quality department. Maybe I need to call somebody from production planning to know the scheduling, then make the decision. What do we need to do? Sort, inspect, rework. Worst case, notify the customer there's a bad shipment on the way. And then we move on to root cause analysis. This is pretty much the same as the root cause analysis helix. It's just another display. Describe and quantify the issue. Gather data and form a tentative hypothesis. Evaluate it empirically. What do the results indicate? Do they support it? If not, form a new hypothesis based on our new knowledge. Worst case, my new knowledge is simply, my hypothesis was wrong. When I do an evaluation of a failed part, I often ask my colleagues when they plan it with me, what will we learn? I don't want to have an experiment where if the part passes, we don't learn anything, and if it fails, we don't learn anything. In one of those two scenarios, we should at least learn something, even if it's just hypothesis was wrong. Also valuable information. If it survived testing, evaluate it. Make sure your root cause is the true root cause. Now this is maybe an oversimplification because I'm not mentioning 5 why here. You may need to go back and repeat the cycle. Now I have the root cause, but why did that happen? And repeat the process. And of course, plan, do, check, act for improvement, a more traditional use. Plan the improvement. Do a small scale implementation of the improvement. And I specifically wrote small scale because if you're going to change a product or process, make sure it's not going to induce new problems. Make sure it's not going to make the problem worse. And make sure it's actually going to fix the problem. Check, was it effective? If not, determine why. New actions are necessary. The process starts over. Or implement the improvements and be sure to seek out further opportunities. If one machine failed due to a problem and we have other machines just like it producing other comparable parts, we may need to implement that same improvement there as well. Update relevant documents. That's shorthand for update your failure modes and effects analysis. Update your lessons learned if you have a lessons learned database. Maybe you need to update your control plans. If you're in engineering, update your design rules. Use the knowledge you paid for that knowledge. If you've spent months working on a detailed root cause analysis, you really paid for that knowledge. Get something out of it. Make sure that failure doesn't happen again in 5 years. Now I'm going to present a couple of very brief case studies of this approach to root cause analysis. The first one is the case of the cracked cable. This was actually one of my favorite investigations. Heavy-duty banded wire cable with the coating was experiencing cracks in the coating. This was a synthetic rubber coating on a wire cable. The problem had been happening over a period of years. Materials experts came in and analyzed it, and nobody could solve it. The problem was test samples were laid out. One of my colleagues, I joined this was an organization I was involved with years ago. My colleague explained to me they hung samples out the restroom window all winter in the expectation that they would crack. Unfortunately, nothing failed. Therefore, they didn't learn anything. Even parts that were not potentially improved did not fail. Therefore, we couldn't trust improvements. Different coating type. An experiment was planned with different coatings. This was a lessons learned for me because I specifically said I want all the samples labeled. Always give very specific details when you put in a request somewhere or plan an experiment, because I said I want labeled parts. I never actually told anybody to put the labels on the parts, so I had a stack of parts that looked alike and a stack of labels. That didn't help much. However, I found out nobody ever looked at the part. So our experiment was exploratory. We cut the end open. It always seemed to have a tear at the end. Looked inside and realized every single crack was happening starting at the same spot. Now I can't prove it started at that because the crack ran through and had two ends, one or the other, but they all seem to have all cracks seem to have a beginning near the end of the cable, so I assume it's cracking and spreading outward. And underneath that cracked area was a very sharp piece of metal in every single case we looked at. This had been going on for years. Nobody ever did what Sheinin said, talk to the parts. Just looking, we found the problem. And once a change was made as an experiment, what happens if we start the metal band elsewhere, not directly over with the coating on top? And the problem never came back. Next situation, I've mentioned quality tools earlier, Ishikawa diagrams, calipers, hammers, that's where this comes into it. Vibration sensor. They were being returned from the customer. These are metallic cylinders with a magnetic mass inside that moves and generates a signal. The problem was there was no signal coming out of some. Best hypothesis I had after looking at the parts was dent in the casing from mounting screw is restricting movement of the magnetic mass because they all had a small dent from the mounting screw. So I wanted to evaluate this empirically. This was not a definitive test, it was an exploratory test. I hooked up failed units to an oscilloscope and they do not generate a signal when moved. New units out of the warehouse did, so I took a new unit and smashed it with a hammer. And it still generated a signal. That dent was much more severe than the small one from the screw, so I had an awkward situation when the production manager walked in and caught me doing that. It's okay, I'm doing science. He gave me a weird look and ran away, but I discovered my hypothesis was wrong. Now, I smashed a 50-euro part. That's not good, but I smashed a 50-euro part and lost 20 minutes of work time. The alternative was I might have spent 2 days, maybe longer, off and on, investigating that. Talking with the supplier about the material, investigating. For me, that 50 euro investigating the wrong hypothesis was an investment because then I had time to move on and continue looking for the correct hypothesis that would actually lead to the root cause. Case of the bushing and bracket failure. This was a plastic bushing inserted to a metal bracket that was failing and resulting in free play in the system. The problem is parts were potentially damaged during disassembly, and even with an endoscope cable going in, we couldn't see what was happening in the system. But I wanted to look at my parts. So I simulated assembly. It's not exact. If something fails during my simulation in a vise, I'm not writing a complaint to my supplier that the part failed, but I gained new information with that. And again, this was a hammer situation because I needed a hammer to push it in, but I saw the movement that was happening. Material loss was moving as it entered the bracket. There's minimal loss, no free play. Heavy loss on both sides, free play. This ended badly for the supplier, good for us, because they needed 8 people on the production line inspecting and doing immediate rework. There were multiple lines producing at the same time. We had to get those parts fixed. Supplier had to take care of it until they could give us a more robust design. And that was just because I looked at the parts. I got that critical piece of information. Not the definitive root cause, but it was enough to move the investigation on to the point where we knew we just need to make a material change. Now I'm going to talk a little bit about customer complaint related root cause analysis. I can't be the only one who's heard this. Something is wrong. We don't know what it is or what part is affected, but you need to do something about it. Now, I'm paraphrasing, but I've encountered that repeatedly. The supplier is going to have difficulties responding to the quality information if insufficient information is provided. The supplier's actions really should be based on facts. To get facts, they must have data. What I'm not saying here is if the customer doesn't provide detailed information, the supplier's off the hook. The supplier has an obligation to ask, but the customer could prevent the loss of valuable reaction time by simply identifying what happened, which part is it, which quantity. The customer issuing a complaint must provide information with this. Which part number? Now, for the supplier, it's better to receive the supplier's part numbers, but generally customers use their own numbers. That's fine. The supplier should be able to find their own part number. The problem is when they name the component, multiples of variations on this are shipped, so nobody knows what unit failed, how many it was it a one-off or a systematic failure? That affects the nature of our investigation. Inventory level. Do we need to do immediate inspections at the customer? And blurry photos serve no purpose. I've actually received a complaint. Immediate actions needed. There was a time change, so my customer's time was ahead of me. They sent blurry photos. It looked like the Loch Ness Monster, in my opinion. We don't produce Loch Ness Monsters. It was just a gray blob. I have no idea what part number it is. I have an idea of what type of part, but not which specific one, so I don't know which line to check. And I don't really know what the failure was because they said see the pictures to see the failure. There was blurriness in the room is the only problem I could see. Sample parts. I'm talking about empirical. Give your supplier that sample part. It's critical for analyzing the issue. Additional information if it's available. What conditions did the part fail under? Was it failed when it was pulled out of the box? Is not the same as it was assembled, in use for 2 weeks, and then returned and failed. The root cause is probably going to be different. They need this information. However, the supplier does have an obligation to ask if it's not made available. The supplier can help minimize the effects of a failure by preparing it in advance. Make sure you have a method in place for the quick recall of a sample part for analysis. The last thing you want to do is start calling around. If you're shipping large quantities, you have a failure, you need the part back, and you have no idea how to get it back. Find shippers in advance. Have a plan ready. If you may need to do sorting at your customer's location, after the failure starts is not the right time to, I was going to say go in the phone book, I might be dating myself, to Google who is the best sorting company in the area near this customer. Pre-plan this. Reach out to these companies in advance. Have a plan ready. Make sure you know who the contacts are. Ensure your in-house people are trained and capable of performing a root cause analysis. Make sure they know how to act. And make sure you have an established procedure, validated, a functioning procedure for quality issues. Train the employees in the procedure. When that part comes back, it's a bad time to start deciding how are we going to approach the issue. There's many processes for that. I'd like to talk about it, but that's beyond the scope of today's talk. And I'd like to briefly reiterate the key points. Empiricism is needed in root cause analysis. This can be achieved by combining the scientific method, Box's iterative, inductive, deductive process, and Deming's Plan, Do, Check, Act. And for me, the most important takeaway from today, please don't forget to look at the part. And now I believe we do have time for questions. So if anybody has questions, please feel free to send them. I'm going to start at the top. First question, has the webinar concluded? No. Just a quick test. Can everybody hear me? Could one person please say test? Okay, that's enough. Thank you. Thank you. I have 4 or 5 tests already. Appreciate that. So next question. Multiple questions are coming in. I'm going to start at the top. Do you have any examples of root cause analysis in regards to data information quality defects? If not, do you think there might be differences in recommended approaches, information, data versus products, software? I'm going to interpret that as something software related or data entry related, data being entered into a program. I don't have any experience in that area, so I'm going to be general and just say I think empirical approaches are also appropriate there. Look at the data that's entered. That might actually be somewhat easier to apply an empirical approach starting out. How many errors are there? How many things have been miscoded? What types of errors do we have? Pareto it, find the worst, and now we need to be empirical. We can't measure the person typing the data in, but go to Gemba. Might be time to start observing the data entry. Can we go over 5 whys quickly? Yes. 5 why. I very briefly mentioned it. For those who don't know 5 why, it's the simple concept of ask why 5 times. The way I look at this, a root cause analysis, there's a failure, something's happened. From my view, there's 2 types of causes, the proximate cause and the ultimate cause. The proximate cause is the cause closest to the failure. It's what we've observed. It's usually the first one we find. And if things go wrong, it's where the corrective actions are set. The problem is, why did that occur? We want the ultimate cause, the true underlying cause that created a chain of failures. I think air crashes. If you're interested in root cause analysis, read about air disasters. Read a book on it or go to Wikipedia. Why did the airplane go down? In many cases, it's a chain of error. You can think of the Alaska Airlines flight MT-80. This airline went down into the Pacific. It was recoverable, and they discovered there was a jack screw on it with the threads are completely worn. Well, the first failure was the stabilizers broke, putting the plane into a dive. Why did the stabilizer break? The jack screw was worn. Now we need to investigate that. You can't close an air crash investigation with the threads on the jack screw are worn. They were completely gone, to be exact. Why were they worn? And the investigation determined they hadn't been greased. That was a serious failure, but why weren't they greased? Well, the company changed the interval inappropriately, so it wasn't going to be greased as often as it should have been. And it wasn't greased even within the interval. Why? Because it was only accessible through a very small hatch that one needs to go up in a bucket loader to reach, and it wasn't visible. There was a chain of failures. Without that 5 why, we don't dig down deep enough. And now I'm scrolling up to the next question. How important is it during the root cause analysis portion to interview the folks who produced the part? If you can, I'd call it incredibly important. Get as much information as you can. I'd hate to leave them out of it. Generally, if it's what I would recommend is, if at all possible, go interview them. They might be able to tell you what happened. Imagine if you spend days with a large team analyzing the issue when a production operator knows exactly what the cause is. You go talk to them and they tell you, I've been complaining about that for weeks and nobody fixed it. It is very important to talk to them. Go into production. I may have mentioned that before. Go to Gemba, go into production. Well, please, what I neglected to mention is while you're there, turn around and talk to the operator if you can identify them, not finger pointing, because that's 5Y. And that, let me go back to the question on 5Y. Operator error, the operator forgot. Why? Well, maybe they were tired. Now, why do we have a process that made it possible for that failure to happen if a person did not remember? Can we make it more robust? Definitely talk to them. Are the slides available offline? I don't know. That would be a question for Adam.
So I'll take this opportunity to break in here, Matt. Sorry, just to interrupt briefly. Several people have asked about the slides. So this presentation will be posted on the Statistics Division's YouTube channel, and so you can go back and revisit it there. I'll talk to Matt after the webinar about seeing if we can also get the slides to put on our website, but I'll do that after the fact. But definitely this will be on our the video will be on our YouTube channel. So.
Okay, thank you, Adam. The next question is a great one. I really appreciate this. How do you determine the ideal size for a root cause analysis team, I assume? Well, ideal size 2 to 20 off the top of my head. The ideal size should be for your issue. What resources do you need? And I said 2, half tongue-in-cheek, because I started out on night shift quality, which meant that team consisted of me and whichever operator grabbed me because they had a problem, and we needed to settle it fast. There's no going back to the office to brainstorm with the operator. They had to keep the machine running. Those were the only available resources, unless we held the problem over into day shift. So your proper team size, I would say, what resources do you need? And the way I approach root cause analysis, usually I have 3 groups. I have my core team, who do I want in every meeting? The supporting team members. I might need a production engineer, but I don't need the production engineer every time. I might need the production operator, the actual machine operator, and I need to clear it with their supervisor to bring them into my meeting. I might not be able to bring them into every meeting, but I see them as in a supporting role. If I'm not interviewing them on the line, we might have them sit in the actual meeting as a supporting member. And of course, your customer or supplier should be considered as well, even if they're not in every meeting. But the real determinant, what resources do you need? Do you need one person to just do legwork carrying around parts? Okay, that's an extra warm body you're going to need. What knowledge do you need? If you have a metal part you may need that's been machined and it failed, you may need a machinist or a machining expert. You might need an expert in the process itself. You may need a metallurgist. Correct. I'm not sure what was, but I appreciate it. Thank you. What is the best mix of common sense and data? I'm really not sure how to answer that. So I'll go with always use common sense and as much data. So I would recommend, I don't think there's a trade-off between I think I understand what you mean now. Common sense, I'm interpreting here to mean what everybody knows and believes, and data. If I'm correct, hope I'm correct, because that's how I'm going to explain it. Common knowledge, common sense, what we all believe to be the case versus data. Like if I had the same failure 7 times in a row because something seriously went wrong with our corrective actions, I'm going to think the 8th time that might be it, but that's just a hypothesis. I'm not going to immediately say it's a reoccurrence. Or here's a scenario. The last 3 times it was the same problem. After the first time we implemented the corrective action and the next parts came back, produced prior to the corrective action. The fourth part that comes back, well, probably common sense tells me it's the same one. I still want data to verify it. Think of it this way: trust but verify. Get the data to confirm it. Our first ideas, our first brainstorming is probably more on the common sense side. List these in the Ishikawa, but we still want data to make sure what we know really is so. There's a saying attributed to just about everybody on the internet. It's not what you don't know that's the problem. It's what you think you know that ain't so. Same applies to root cause analysis. Can you email a copy of the presentation? I believe that's already been covered. Okay, now I've got a long one to read to you. How do you know how far back to go? Out of specification test result, incorrect instrument setup, operator inattention, overworked operator, improper staffing, financial restrictions, greedy owner. Where does it end? Where is the root cause? The simple action is where you can set the corrective action and ensure the chain never comes back. And I say that's the simple action because if you had an inattentive operator and you tell them pay attention and you believe they really will do it sincerely, you prevented the reoccurrence, but that really isn't 5Y or deep enough to make sure the problem truly never comes back. My explanation for my colleagues, I call it the point of absurdity. When if we dig any deeper, it doesn't make any sense. We can't go any deeper or the answer is just ridiculous. What point should we stop at where we know this failure will not reoccur here on a comparable system or in the future? When you get back to the greedy owner level, if you have a solution for that, I think that of itself is a webinar topic, explaining that solution. So I would say, I can't do anything about that. Financial restrictions, can you do anything about it? Can you persuade someone to free up finances? If not, you can't do anything there. Find the point where you can implement your corrective action. And I think we have time for just one more quick question. And if I scroll down, I can see it's already there. What are your thoughts on several root causes? Everyone seeks out a single root cause, but sometimes you have interaction. I would dare say often. Let's go back to air crashes. The Air France flight that went down off the coast of Brazil. It was caused by a spigot that iced over. The sensor didn't work. The pilot got the wrong reading. That wouldn't bring the airliner down. The pilot did the wrong reaction. Had the pilot reacted wrong with the right sensor, they could have recovered. Bring the two together and it fails. That's something you definitely need to be aware of, but I'm not going to cover that in the 2 minutes I have remaining.
You want to try to take one more question and then
looking right now. I've only got time for one more, so I'm going to have to pick a short one. How do you get others on board with verifying? I wish I picked an easy one. With making sure you have the root cause. I'm sure it's sincere, but others in your team have incentive. We found the root cause, let's call it and close the issue. Why? Because they have other things to take care of. They have their regular job to do. They want the customer off their back. They want management to say, good job, you're done, go do the rest of your work. My short answer would be try to explain to them the consequences of being wrong. Imagine you close out a major issue. You just told the director of the company, we got it, it's gone. You let your customer know. It's going to be very awkward when that issue comes back in 3 weeks. And if you don't consistently dig down deep enough, sooner or later, it's going to come back. Okay, and it looks like I'm out of time. Thank you. Adam?
Yes, thank you. Thank you very much, Matt. Excellent presentation, just terrific. To the rest of our attendees, we ask that you complete the short survey at this time that's available within GoToWebinar. A recording of the webinar will be available, I've said this already, within a few days on the Division's YouTube channel at youtube.com/ASQStatsDivision. Please be sure to share with this webinar and other archived webinars with your friends, coworkers, and colleagues. We also encourage you to have a look at the division's LinkedIn page as well as our events calendar, which can be viewed at asq.org/statistics for the latest news on webinars, conferences, and many other topics. That is all the time we have for today. Thank you, everyone, for joining. And thank you again, Matt, for presenting with the Statistics Division. I hope everyone has a wonderful afternoon, and Matthew, a wonderful evening. Thanks again. Goodbye.
Okay, thank you, Adam.